Previously, we covered the core foundations. Now in part 3, we tackle main asteroid belt. Why the belt is not a failed planet. Last episode, we covered where the main asteroid belt actually sits and what kinds of objects you find there. Today's question is this: why didn't all that material ever become a planet? And why does that matter for understanding Earth? People look at the asteroid belt and assume it must be the wreckage of something. A planet that got smashed apart, maybe, or a world that almost formed before getting interrupted. It's an intuitive idea. There's clearly a lot of material out there between Mars and Jupiter, spread across a ring roughly 1.5 to 3.5 astronomical units from the Sun. Surely that should have become something. It didn't. And the reason why tells us something fundamental about how our entire solar system was assembled. This is Orbital Dispatch, and this is the main asteroid belt, Episode 3. Let's start with the numbers, because the first thing that surprises most people is just how little material is actually in the belt. If you added up every asteroid, every rock, every fragment in the main belt, and compressed it all together, the total mass would come to roughly 4% of the Moon, not 4% of Earth, 4% of the Moon. That's extraordinarily small. The entire belt, spread across hundreds of millions of kilometers of space, contains less material than a single modest moon. That fact alone should put the destroyed planet idea to rest. There's simply not enough here to have ever been a planet. Even if you somehow gathered every belt object together, you wouldn't get close to building something worth calling a world. So whatever happened to the belt, it wasn't destruction, it was prevention. Which raises the harder question: if there was never a planet there, why not? The inner solar system formed from similar material. Why did this particular region fail to accumulate? The answer involves Jupiter, and it's more nuanced than you might expect. To understand what went wrong in the belt region, you need to go back about 4.5 billion years. The Sun had just ignited and was surrounded by a rotating disk of gas and dust, the protoplanetary disk. Within that disk, material was gradually clumping together through accretion. Grains stuck together, became pebbles. Pebbles became boulders. Boulders became planetesimals. And eventually some of those swept up enough material to become planets. That process worked well in the inner solar system, where conditions were right and timescales were short. It also worked well in the outer solar system, where enough mass existed for giant planets to form quickly before the disk dissipated. In the belt region, though, there was a problem. Jupiter. Jupiter formed early, and it formed fast. Current models suggest it reached something close to its full mass within the first few million years of the solar system's history. Once it was there, it began doing something very specific to the belt region. It started stirring it. Jupiter's gravity resonates with objects at certain orbital positions. These are called mean motion resonances. They occur where an asteroid's orbital period is a simple fraction of Jupiter's. An asteroid that orbits the Sun 3 times for every one Jupiter orbit, or 2 times for every one, receives a regular gravitational nudge at exactly the same point in its orbit, every single time. Those nudges accumulate. Over millions of years, they push objects into increasingly elliptical orbits, ones that eventually cross Mars, cross Earth, or send objects deep into the inner solar system. Those resonance zones carved gaps in the belt, and those gaps are real and visible today. They're called the Kirkwood gaps, named after Daniel Kirkwood, who identified them in the 19th century. The belt isn't a smooth, uniform ring. It's punctuated by empty corridors at specific distances. But Jupiter wasn't just clearing gaps. Across the whole belt region, it was also preventing accretion. Here's the thing about planet formation. It needs gentle collisions. 2 planetesimals that meet at low relative speed can stick together, grow, and gradually build something larger. Stir those orbital velocities into high eccentricities and steep inclinations, though, and collisions stop being constructive. They become destructive. That's what Jupiter did to the belt. It raised collision velocities to the point where impacts no longer built things up. They ground them down. The same material kept colliding, kept fragmenting, and the total mass in the belt slowly eroded rather than accumulated. This process is called dynamical excitation, and it explains both why the belt failed to form a planet and why it now contains so little mass compared to what models suggest was originally there. The belt's original mass may have been 10 to 1,000 times what's left today. Jupiter didn't just stop it growing, it scattered most of it away. Now here's something worth sitting with. The composition of what remained preserves a record of conditions at different distances from the Sun during that early period. And that record has turned out to be genuinely important. The belt isn't uniform. Objects in the inner belt, roughly 1.5 to around 2.5 astronomical units, tend to be silicate-rich. These are the S-type asteroids, broadly similar in composition to the rocky inner planets. They formed in a warmer part of the disk, closer to the Sun. Further out, from around 2.5 to 3.5 astronomical units, the objects are darker and carbon-rich. These are the C-types. More primitive in composition, meaning their chemistry hasn't been radically altered by heat or geological activity. They preserve material from the very early solar system, hydrated minerals, carbon compounds, and in some cases, organic molecules. This gradient across the belt is exactly what you'd expect from material that formed at different temperatures within the disk. In that sense, the belt is a fossil of early solar system chemistry, frozen in place. But here's the open question that planetary scientists are actively working on. How did the belt become mixed? The neat gradient gets complicated by the fact that you can find C-type objects in the inner belt and S-type objects further out. The two populations aren't as cleanly separated as they should be if everything stayed where it formed. Something shuffled them. The leading explanation involves large-scale planetary migration early in the solar system's history. Giant planet migration models, including variants of what's sometimes called the Grand Tack hypothesis, suggest Jupiter may have moved significantly inward, then back out again, during the first few million years. As it did so, it scattered objects from the outer disk into the belt region, seeding the inner belt with material that originally formed much further from the Sun. This is still an area of active research and isn't fully settled. But the mixed composition is real observational evidence that something dramatic rearranged material across the solar system during its earliest phase. So what does any of this mean for Earth? More than you might first assume. The C-type asteroids, the dark, carbon-rich, primitive ones, are among the most chemically interesting objects we can study. They contain water, locked up in hydrated minerals. They contain organic compounds. Some are considered close relatives of a class of meteorites called carbonaceous chondrites, the most chemically primitive rocks we have access to. Current evidence suggests a significant fraction of Earth's water arrived relatively late in the planet's formation, delivered by impacts from water-bearing objects. The belt, particularly its outer C-type population, is one of the plausible source reservoirs. The isotopic evidence from carbonaceous chondrites is one of the main lines of argument here, though the picture isn't yet complete. If that's correct, the belt didn't just fail to become a planet. It helped deliver ingredients to the one we live on. Two missions are particularly relevant here. Dawn, which operated between 2007 and 2018, orbited both Vesta and Ceres, and gave us our first detailed look at two of the belt's largest and most geologically distinct bodies. Ceres showed evidence of briny water near its surface. Vesta turned out to be a differentiated body with a metal core, closer in nature to a small planet than a typical asteroid. Then there's Hayabusa 2, the JAXA mission that returned samples from the near-Earth asteroid Ryugu in December 2020. Ryugu is a C-type, and the samples it brought back contained amino acids and hydrated silicates. Direct physical evidence that carbon-rich asteroids carry organic and water-bearing chemistry. Analysis of those samples is still ongoing, with results continuing to be published. So let's bring this together. The main belt isn't the remnant of a destroyed planet. It never had enough mass to form one, and the reason it didn't accumulate more comes down to Jupiter. Jupiter's early formation stirred the belt region, raised collision velocities, and turned what could have been a constructive process into a destructive one. Over hundreds of millions of years, most of the belt's original mass was scattered away, leaving the thin, low-mass population we see today. What remained preserves a record of early solar system chemistry. The gradient from silicate-rich inner objects to carbon-rich outer objects reflects conditions in the protoplanetary disk, and the mixing of those two populations hints at large-scale planetary migration that reshaped the solar system during its earliest phase. Far from being a failure, the belt is one of the most informative places in the solar system. A fossil record, a plausible water reservoir, and a window into conditions that no longer exist anywhere else in our neighborhood. Next episode. Part 4 looks at the families within the belt, what they are, how they formed, and what they tell us about the collision history of the inner solar system. The full playlist is linked in the description if you want to follow this series from the beginning. And if this kind of careful, science-first content is worth your time, subscribing is the best way to catch each new episode as it comes out. That is part 3 of Main Asteroid Belt. Subscribe so you do not miss it.